When it comes to creating DC circuits, like I do in around 90% of the cases, then the function of the most basic passive components, the resistor, the inductor and the capacitor, is pretty straightforward. The resistor, like the name implies, resists the current flow, and thus can be used, for example, in an LED circuit to convert the excess power into heat, so that our LED can shine with the correct nominal current flow, unless of course someone evil shorts the resistor. On the other hand, you can find capacitors and inductors in DC circuits as energy storages, because the capacitor resists sudden changes in voltage and the inductor sudden changes in current, and thus we get a smooth output voltage from, for example, power supplies. But make sure to watch the individual basics episodes for those three components if you want to learn more about them. What is important though is that resistors resist the current flow in a DC circuit, while inductors and capacitors do not influence the DC current flow, unless of course we talk about switch on/off situations. But DC is not almighty. While looking around us, we can see tons of applications where we got AC voltages. Most importantly, our sinusoidal mains AC voltage. So in this video, I will tell you about the basics of impedance, which in a nutshell is the concept of resistance extended to AC circuits, where now inductors and capacitors play an important role as well. Let's get started. This video is sponsored by JLC PCB. One piece of news about them. JLC PCB will shorten the lead time of green 2-layer standard PCBs in the near future. So feel free to test out their PCB quality and fast delivery speed for a low price. For the experimental setup, I connected my function generator outputs to the inputs of an amplifier. This way, by varying the frequency and amplitude of the function generator sine wave, I get the amplified sine voltage at the output of the amp that can handle a much higher power outputs, which means we can know components up to it. For starters, let's use this small inductor, which features an inductance of around 214 microhenry. By connecting it directly to the sine wave, which features an RMS voltage of 6 volts and a frequency of 10 kHz, and observing the occurring current flow with a current clamp, we can firstly see that the voltage wave is leading in comparison to the current wave, with a phase shift of around 90 degrees, and also that an RMS current of 203 mA is flowing. That means that this time the inductor does not create a short circuit like it did with DC. It resists the current flow, just like a resistor would do, and thus this value is measured in ohms as well, and is called the inductive reactance. This new kind of resistance originates from the fact that the constantly changing magnetic field of the inductor opposes the current flow, which is also the reason why the voltage is leading with a phase angle. And by increasing the frequency of the sine voltage, we can see how the current RMS value slowly decreases, which means our inductive reactance increases with the frequency. The final equation for it is 2 pi FL, with the frequency and inductance being the most important variable values. Now if we would replace the inductor with a capacitor, which features a capacity of 1 microfarad, and use a frequency of 3 kHz, we can once again observe a phase shift of around 90 degrees, but this time the current is leading. Also, we got an RMS current flow of 110 mA, which means just like with the inductor, we got a new sort of resistance, this time known as capacitive reactance. Its cause is the constant charge reversal of the electrostatic field of the capacitor, and its equation once again features the frequency and capacitance as the most important variable values. This time though, with higher frequency, the current flow increases, which means the capacitive reactance decreases. Now if we go back to the plain old resistor and hook it up, we can see that it does not create a phase shift, and its resistance and thus current flow is not dependent of the AC frequency. It still only got its ohmic resistance. And just like that, you're now familiar with the reactance of the inductor and capacitor, which not only changes the magnitude of the current flow, dependent of the frequency, but also affects the phase angle between voltage and current. And of course, we still got our ohmic resistance, which only influences the magnitude and not the phase. But the question remains, what does all of that have to do with impedance? Well, let's imagine we put a 50 ohm resistor and a 1 microfarad capacitor in series to the 3 kHz 6.1 volt sine voltage. How can we calculate voltage, current and phase angle values? Simply adding the ohmic resistance to the capacitive reactance and calculating with that would only deliver wrong values. And thinking the phase angle would stay at 90 degrees is also incorrect. The solution is to turn both values into a complex impedance and calculating with that. This one is the polar form of the impedance, but also important for calculations is the Cartesian form. In it, we can see our known values for the resistance and reactance, but there's also a J. This J is actually the imaginary unit I of the imaginary number system, but since I usually refers to current in electronics, we stick to the J. If we would now draw a complex plane with the x-axis being the real axis and the y-axis being the imaginary axis, we could now plot our resistance and reactance. The resistance is obviously real, so we go with a value of 50 ohms to the right. The reactance, however, is imaginary, meaning we go 53 ohms down. And by the way, if we would use an inductor instead of the capacitor, the direction of the arrow would be inverted, so upwards. But anyway, the now emerging arrow is the impedance vector we've been looking for. Its angle is required for the phase angle and its magnitude for the current calculation. So according to simple trigonometry, the magnitude equals the root of r squared plus xc squared, and the phase angle is arctangent of xc divided by r. And by using my trusty old TI-83+, I calculated a magnitude of 72.9 ohms, which equals a current flow of 83.7 milliamps, and a phase angle of 46.7 degrees. By measuring the corresponding values at the practical circuits, we can see that our calculations were actually not too far off. They cannot be perfect, however, because our capacitor itself not only featured capacitance, but also a small resistance and even a super tiny inductance. Those values are known as equivalent series resistance and equivalent series inductance, and basically build up a complex impedance even without an additional resistor. In the case of the capacitor, they were rather small, but if you would look at a practical inductor, then you can see that the previously measured reactance is far from the calculated value, meaning it got tons of parasitic resistance. And by the way, by utilizing a good LCR meter, you can not only measure the capacitance, resistance and inductance, but also the complex impedance with its magnitude and phase angle, but only for certain frequencies. But anyway, through the impedance concept, we could now not only calculate the current, voltage and phase values for such a simple circuits, but more complex ones as well. But then again, you would need to be familiar with a bit more complicated math, which was definitely not the point of this video. The point was for me to show you that when it comes to AC circuits, the combination of inductance, resistance and capacitance changes the magnitude of the current and its phase, which can offer challenges for electronic designs. But due to the concept of impedance, it is something we can easily understand and calculate. And with that being said, I hope you learned something new through this video. If so, don't forget to like, share and subscribe. Stay creative, and I will see you next time.